Hi, this episode is about chapter 14 of this SEG publication, which looked at Machangqing copper molybdenum porphyry systems. They're located at southeastern part of Tibet. At Machangqing, the story really comes down to three key intrusions. The barren granites, dated about 34 million years. The ore-forming porphyries at roughly the same time, 34.3. And the mafic Lamprophyres just a little earlier, around 36.5. That sequence set the stage for a complex porphyry, copper, molybdenum, and gold system. The deposit style here is textbook, but with a twist. We can see potassic alteration at the core with zoned hydrothermal stages stretching from skarn to supergene, and mineralization that runs from veins to disseminated ores. And what's striking is that the ore bodies are hosted both in the porphyry stocks and in surrounding Paleozoic sedimentary rocks. It shows how fluids pushed far beyond the intrusions themselves. To put this together, the team used a whole toolkit of analytical methods. Zircon uranium-lead dating, which nailed down the timing. In situ rubidium strontium dating of phlogopite and amphibole gave additional age and isotopic control. Whole rock geochemistry through XRF and ICP-MS, which mapped out major and trace element signatures. Strontium neodymium isotopes helped fingerprint magma sources. Apatite chemistry, which tracked volatile elements like sulfur and chlorine, and in situ strontium and oxygen isotopes in apatite tied those volatiles back to their magmatic origins. In other words, it wasn't one method, but a combination of all these techniques that unlocked the story here and showed that how barren granites, fertile porphyries, and volatile charged Lamprophyres came together to build one of the most instructive porphyry systems that we know. Here we have a geological map of western Yunnan. Over here the crust has been squeezed, twisted, and re-energized by magmas that surged up after the big tectonic collision. And right in the middle is the Jinsha-Jiang Aleutian suture zone, which is basically the scar left behind when the India slammed into Eurasia. But instead of crust shutting down, it fired back up. It started melting, and out came potassium-rich magmas that cut their way up. Those magmas lit the fuse for massive porphyry, skarn, gold, and copper deposits. Names like Machangqing, Yalung, and Palang deposits. On this map, the green spots show where those potassium-charged magmas broke through, and the yellow diamonds mark the ore deposits they created. Here is a zoomed-in map, which shows a mosaic of intrusive units, each linked to a unique magmatic pulse. The central granite porphyry, which is shown in pink, is the main host of copper, molybdenum, and gold mineralization. Around it you see monzonite, syenite, and Lamprophyre dikes, each representing a separate melt source of intrusive episodes. The Lamprophyres are especially important, cutting across the entire complex. They carry the signature of deep volatile-rich magma inputs, and they were in place before the main porphyry event. The red stars mark sampling locations. These were the sites where apatite crystals were collected. From them, the study showed that mantle-derived Lamprophyres contributed unusually high levels of sulfur and chlorine to the porphyry system. Unlike some classic porphyry systems, this map doesn't show a clean lateral zoning pattern where molybdenum, copper, and lead and zinc line up in neat bands. Instead, Machangqing's signature lies in its stacked and mingled magmatic bodies. The closely spaced intrusions over a span of about 3 million years built up the fertility of the whole system. And one of the key concepts here is that Lamprophyres often arrive in multiple pulses. The earliest phase, dated to around 36.5 million years ago, represents the first mafic recharge from the mantle, but later Lamprophyre dyes can intrude even younger granites, reminding us that volcanic plumbing system is never static. A chamber can keep receiving injections of mafic magma, periodically spending up new eggs. The idea of this idea of multi-phase pulsed Lamprophyre intrusions is a plausible geological explanation for the Machangqing system. It has not been explicitly stated in this study, but it fits the broader picture of how post-collisional porphyry systems can be recharged, reconfigured, and ultimately made fertile systems. One of the unusual features of this system is the presence of hornfels hosted molybdenite, as we can see in panel D. Instead of being restricted to the porphyry or skarn zones, molybdenite actually overprints hornfels. This is less common in other porphyries and shows that hydrothermal fluids migrated far beyond the porphyry body into altered wall rocks. And the implication is a wide hydrothermal footprint, which is likely driven by volatile-rich system which sustain fluid flow. And it reinforces the idea that Machangqing was unusually fluid saturated and capable of aggressively penetrating its surrounding rocks. Another point of interest here is the skarn type magnetite shown in panel C. Skarn magnetite is often found in copper gold skarns. It's less expected in molybdenum dominant porphyry systems like here. Its presence here highlights the hybrid nature of Machangqing, which is a deposit that combines both porphyry and skarn style mineralization. The galena and sphalerite assemblages shown in panels E through H add another layer of complexity. Lead and zinc minerals are typically confined to distal zones in porphyry systems, but here they are not only widespread but also disseminated and intergrown with chalcopyrite. And this points to a strong lead-zinc halo and suggests that multiple overlapping pulses of sulfide mineralization occurred here. The presence of arsenopyrite with pyrite, particularly in panel F, indicates a more reduced fluid environment and complex evolution that differs from the standard porphyry models. And finally, the textural complexity in the sulfides, as seen in panels G and H, tells its own story. Intergrowths of sphalerite, chalcopyrite, and pyrite display irregular grain boundaries and overprinting textures. These patterns are a sign of multiple hydrothermal overprints and fluid mixing or fluctuating redox and temperature conditions. So, rather than being formed in a single pulse, Machangqing's sulfides appear to record a dynamic multi-stage hydrothermal system. What you're looking here are some really telling features of the Machangqing system. Panel D shows these dark rounded blobs called mafic microgranular enclaves, or MMEs for short. They're basically little injections of mafic magma frozen inside the porphyry, and that's quite unusual for a molybdenum dominant system like this. Why does it matter? Because it proves there were mixing going on. Mafic magma from the mantle mingling with felsic magma in the chamber. That kind of recharge is exactly what can push a system into volatile saturation and kick off ore formation. Panel C is a hand sample of Lamprophyre. These are volatile-rich magmas straight from the mantle, and they don't get the spotlight, but they play an important role. The Lamprophyres came first, and their chemistry ties directly into ore forming porphyries. In other words, they carry the deep-sourced sulfur and chlorine that fueled the whole system. X-ray map images tell the story in even more details. Panel E shows a porphyry thin section packed with amphibole and feldspar, and you can see iron and magnesium phases that point to a volatile-rich environment. Panel F zooms in on one of those enclaves, which is a dense clot of mafic minerals. That's a snapshot of magma mixing in action, and it may have been the trigger for ore fluids to separate out. And panel G from Lamprophyre thin section shows minerals like phlogopite, kalinopyroxene, and iron titanium oxides. And the chemistry screams deep metal origin and high volatile contents. So, what's the big picture? The fertile porphyries at Machangqing didn't just form because of their age or their bulk composition. They became fertile because volatile-rich mafic magmas kept recharging the system. And the enclaves are the fingerprints, and the Lamprophyres were the delivery system for the fluids that made it all happen. What's special about this figure is that it takes us right inside the minerals, instead of just looking at the whole rock geochemistry and chemical results of or even basic microscopic images. We have full spectrum elemental maps: silicon, oxygen, aluminium, magnesium, calcium, and phosphorus. They all plotted at the scale of individual amphibole grains. It means that we are not just seeing apatite sitting in a rock. We are actually watching how elements partition inside and around those grains. The calcium and phosphorus maps make the story even clearer. They light up the tiny apatite inclusions trapped inside amphibole. What's interesting is how localized those bright spots are. They didn't just happen by chance. Apatite crystallized early and got locked in as the amphibole grew around it. That matters because apatite is where fluorine, chlorine, sulfur, and rarest elements get stored. So these little inclusions are like tiny fingerprints of the system's volatile and RE budget. Now take a look at the magnesium and aluminium maps. Magnesium shows strong, almost stripped zoning, a gross pattern tied to changing temperature or fluid chemistry. Aluminium, on the other hand, is patchier, maybe reflecting later diffusion or replacement by fluids. And together they give us clues about the cooling history, fluid recharge, and back and forth interactions that controlled ore fertility. And finally, silicon, oxygen, and aluminium maps bring it all together. You can actually see gross zones, resorption surfaces, and overprinted textures. They are mineral equivalent of tree rings, but more chaotic in these images. It tells us that it wasn't a one and done melt. Machangqing's porphyries were evolving through repeated injections with mixing and volatile overprints. And that complexity is exactly what makes them fertile. This figure dives even deeper into what makes the Machangqing system so thick and enriched. By zooming in on apatite, what stands out immediately is just how much sulfur and chlorine these apatites contain. And that's unusual. You rarely see values this high in porphyry systems. And why does it matter? Because high sulfur and chlorine point straight to a volatile-rich melt. Exactly the kind of chemistry that drives ore forming potential. Another cool detail is that isotope dating was done directly on apatite, shown here alongside elemental maps instead of just giving you an age. This approach ties the timing of magmatism to the geochemical environment. And that means we can link fertility signals to precise events in the magmatic timeline. The element zoning is where it really gets interesting. Chlorine shows clear banding and zoning patterns, while fluorine is more uniform. And this tells us fluids were evolving over time, likely through cycles of degassing and recharge. Apatite here is acting like a recorder of fluid history, freezing in those subtle chemical shifts. And then there are the supporting maps: sodium, magnesium, oxygen. These don't always get reported, but together they fill in the picture of melt composition and crystallization. The big takeaway here is that apatite is not just a minor accessory mineral. It's a key to unlocking how volatiles moved, how fluids evolved, and why this porphyry system ended up fertile. Here we have dating results. Panels A through C show zircon uranium lead dating for barren granites, for porphyry intrusions and Lamprophyres. The granites come in at about 34 million years, porphyries, roughly around 34.3, and Lamprophyres just a bit older at 36.5. And that's a very narrow window in geologic terms. It suggests that these very different rock types, barren granites, fertile porphyries, and volatile-rich Lamprophyres, were all part of the same magmatic tectonic pulse. And instead of evolving in isolation, they may have tapped into shared reservoir. The Lamprophyres are especially interesting here. They bridge a sequence showing slightly older ages but still overlapping within error, and they are dated in two different ways: uranium lead in zircon and rubidium strontium in phlogopite. And both systems give consistent results, which strengthens the case that these mantle-derived magmas arrived early and likely recharged the system. If Lamprophyres were injecting heat, volatiles, and metals into the crust, they could very well have triggered porphyry mineralization. Now look at panel D. The rubidium strontium isochron gives an age of about 36.5 million years, which matches the zircon data, but MSWD, basically the scatter, is unusually high at 7.4. That's a clue that the isotopes were not all behaving in a clean, closed system. Instead, it hints at real geological complexity, maybe open systems, strontium mobility, mineral zoning, or mixing between mantle and crustal melts. Rather than being an error, that scatter tells us the system was messy, fluids and magmas interacting dynamically. And finally, some of the Lamprophyres show really radiogenic strontium, with strontium ratios pushing up to 0.84. And that's far higher than you would expect for a straight mantle melt. It suggests either a strong crustal influence or an enriched mantle source that had already been modified by subduction. Either way, it reinforces the idea that the Lamprophyres were not just simple mantle injections. They carried a mixed, enriched signature that played a big role in fertilizing the porphyry system. All three major intrusive phases at Machangqing, the barren granites or forming porphyries, and the volatile-rich Lamprophyres were in place within just about 3 million years. That's a really tight window, as I said before, and it gives us a rare time-resolved snapshot of magmatic evolution, which is tied directly to mineralization. Now, even though the Lamprophyres are the oldest, they turned out to be critical. They were loaded with chlorine and sulfur, acting almost like volatile granites. By recharging the deeper magma chamber, they likely set off the processes that made the porphyries fertile. Their isotope signatures, strontium and oxygen in particular, match those of porphyry apatites, confirming the genetic link between them. This also answers a big question: why were the porphyries mineralized while the granites, which look almost identical, were barren? The difference comes down to volatile enrichment and magma mingling. Porphyries contain abundant mafic enclaves and higher sulfur and chlorine contents. They're all pointing to active interaction with Lamprophyres. The granites simply don't show that. And then there is apatite. They preserved sulfur and chlorine contents that captured the volatile fingerprint of the system, and their strontium oxygen isotope composition helped reconstruct the fluid pathways. In effect, apatite provided the forensic evidence linking the Lamprophyres to the fertile porphyries. For exploration, the message here is clear. By integrating zircon and phlogopite dating, multiple isotope fingerprints, and trace element geochemistry, geologists can distinguish fertile intrusions from barren ones, even when they look the same in the field and were in place at the same time. So, in the end, Machangqing is not just another copper molybdenum gold deposit. It's a model system showing how mantle volatiles, crustal melts, and careful geochemistry converge to create mineral wealth. Thanks for watching.